Hi, everyone. This is Nalini Elkins with Inside Products. I hope you can hear me okay. Maybe somebody can send me a quick note to let me know that you're hearing me, and we'll go ahead and get started. So, again, I'm Nalini Elkins with Industry Network Technology Council, and we are fortunate today to have Carsten Bormann speaking to us. By the way, the meeting is being recorded, just FYI. And you know, Carsten is one of these people that I'm just going to say as a sidelight. You know, I've seen him present, and I know I have said a lot of times, I want to grow up and be like Carsten. He just is just incredible in terms of how he makes very, very complex things, even understandable to somebody like me. So I'm just very, very happy to have him. And what he's going to do is give us an overview of this landscape. As you know, it's a very fast-moving and growing landscape, this whole IoT business. And this is what Carsten has been thinking about for many, many years. As he says, he likes bringing the internet to odd places. And some of the things in the IoT world are certainly quite odd. So he's co-authored or authored many RFCs. He knows, as I say, he's going to tell you a lot about all the various bits and pieces of the IoT world and how they fit together. This is a little bit about our series. So we've got 5 sessions. Today is the introduction, and then May 12th we continue with 6TiSCH, DetNet, and so on, and keep going. This should really bring you up to date on a lot of stuff as to what's going on. There will be a MOOC as well, and when that's available, we will go ahead and announce that. And so this is these webinars are funded through the generosity of ISIF Asia. It was a grant to the India Internet Engineering Society. Thank you so much for your continued support to ISIF Asia. And we are, INTC is a collaborator with them. And so we are fortunate to be working together. With that, I will not keep you any further. I will go ahead and turn this over to Carsten. I'm going to make him the presenter. So Carsten, you are on.
Thank you for the introduction, Nalini. So it's a pleasure to talk to you, whatever time of day it may be for you. It's early evening. For me, it's probably early morning for Nalini. So it's nice to be able to do these webinar things. If you want to look at the slides, an earlier version of the slides is at slides.cabo.space, and I will upload the slides I'm using right now right after the webinar. So just take note of that URL. I'm sure that the webinar will have an official way to get these slides, but just as a quick way for you to find them, here they actually are. So let's quickly talk about myself. Nalini said a lot of things about how wonderful I sometimes can be, but very little about what I do. And I'm with Universität Bremen in Germany, in the Center for Computer Technologies, where we try to do meaningful research that actually can be used in the industry. And in the IETF, I currently chair the Constrained RESTful Environments working group, the CoRE working group, and the Thing-to-Thing research group. And if you want to know more about all that, there's a reading list for you. So those are the RFCs. You may want to take a screenshot and start reading them. But maybe it's easier to just show this one slide here. So what I have been doing the last 35 years can be summarized as bringing the internet to new applications. And that usually works the following way. I talk to domain experts and they explain to me why the application X can never run on the internet. And then the internet works on the application, and about 10 years later, the domain experts actually ask me what's the best way to turn off the remaining parts of X that still aren't on the internet. So that happens again and again. And I think it's a little bit like the anecdote that there were a lot of scientists who had were able to prove that airplanes cannot fly. Yeah, just making them fly was helpful in proving them wrong. So what is this IoT thing? The idea behind the IoT is that a long time ago, when communications industries started, the idea was to connect places. So you had telephone cables strung from one building to another. And that was pretty much what they did the first 100 years. But then mobile phones came out, and it turned out that you actually do not want to talk to buildings, you actually want to talk to people. And that, of course, also increased the number of points that want to communicate a lot. And what has happened since the start of the century is that we actually want to talk to things as well. So we are now talking about 50 billion or 100 billion or 200 billions, depending on who you talk to, of things that actually use the internet to communicate. And for the people who do the standardization in this space, the IETF people, this is kind of normal business. We are scaling up things all the time. So the Internet of Things means we have to scale up the number of nodes yet again into a 2 or 3 digit billion number of billions. But there's one aspect to this that is a little bit new, and that's actually scaling down. You cannot have 200 billion nodes if each of these consumes a watt. Well, maybe you can, but that's very expensive, and we want to cut down on energy usage. So we really have to find ways to work with nodes that have reduced requirements. So reduced cost, reduced complexity in creating them and in managing them, in installing them and taking them down when they have done their job. And this scaling down is an important aspect of doing the Internet of Things. So we are learning a few terms again that we seem to have forgotten, like kilobyte or megahertz. So I have students who sometimes have trouble distinguishing between megabytes and gigabytes, but don't even know what a kilobyte is. And similar with megahertz, CPUs are gigahertz these days, but in this space, maybe a few megahertz is good enough to run your toothbrush or whatever you want to connect to the internet. And again, the cent, this cannot be expensive. It cannot be as expensive as a new laptop or a new phone to connect everyday items to the internet. And this scaling down also means that the compute we have available to us is rather limited. So about 10 years ago, when we did RFC 7228, which essentially defined the term constrained nodes, we looked at the landscape and we found that there is a big cluster of items that have about 10 or 16 low 2-digit number of kilobytes of data and a low 3-digit number of kilobytes of code. And these devices actually can talk to the internet. We call them class 1 devices. We know that there are smaller devices, but they are really too small to be their own citizen of the internet. They need help from something else. And of course, we also have larger devices. So these 1000 nodes are really bottom line. And in many applications, it's worthwhile to maybe pay another $1 per device and go up in compute. But the point is that we actually want to be able to talk to these devices here. And to someone who has been doing this kind of thing for a long time, this is a PDP-11, and it probably had about 100 kilobytes of code. It had a little bit more of 10 kilobytes of data space. Well, it also had tape drives, which probably had a whopping 34 megabytes or so, but that's not what I mean today. Essentially, the compute that is in that rack is going into these IoT devices. That's what we have. And remember, the internet was built out of devices like the rack that I showed. So this should all be very much possible. One interesting observation here is that in the constraint space, we have much less going on in the way of Moore's law. And the reason for that is that any gains that the remaining years of Moore's law are giving us are usually used to save power and to save cost, not to increase performance and power. So these numbers do grow, but they grow very slowly. It's not like in application development where you can say, oh, my performance problem right now will be history next year when there will be systems that are twice as fast. So from these constrained nodes, we build constrained networks. And what turns out to be a problem in these networks is it's hard to do networking with very little power. So if we don't want to change batteries in these devices all the time or charge batteries all the time, we need to make sure that these devices actually can sleep. So they don't have to listen to the network all the time. And that means that networking in this space feels different than between laptops and smartphones and servers. The networks we get in the constraint space are usually on the order of 100 kilobits per second or a couple hundred kilobits per second. There may be high loss just because you cannot invest in wonderful antennas. The picture here shows big antennas coming out of the device, but your typical IoT device is not going to have such a big antenna. It's some trace on a printed circuit board, and well, yeah, you have high loss. You also have high link variability, because if somebody touches the device just in the place where the antenna is, then the quality goes down and so on. So essentially, an unstable radio environment is relatively typical for an IoT device. And there may also be other limitations, such as the size of a physical layer packet, or also functions like multicast and so on may not be available in such an environment. So when we are talking about networks here, we mostly are talking about special low power networks like ZigBee, Bluetooth Smart, Z-Wave, DEC ULE. But of course, the whole thing also works on Wi-Fi, but maybe not at the microwatt level, but then it will be more expensive. But that's of course part of the picture as well. So constrained node networks are networks built from constrained nodes, where much of the network constraints comes from the constraintness of the nodes. So there are other constrained networks like space networks, where the fact that the network is somehow constrained has to do with other issues like a few million kilometers you have to cross. But here really the constraintness mostly comes from this constraintness of the nodes. We have a few other terms for this, LLN or smart objects, and so on, but I want to focus on the term constrained node networks for now. So how does IP come in here? We have a lot of experience with putting IP into application domains that up to then had some very specialized communication technology. For instance, the telephone for a long time had some very special time domain multiplexing circuits. And there were good reasons why they started out with those. And actually, IP could only start to replace them at a time where computer memory was cheap enough that you no longer needed the really strict real-time requirements of TDMA networks. But yeah, those improvements, this progress actually happens. And when you talk to application experts, domain experts, they will always have some problem that they think the internet is not good enough for. And of course, the answer is to make the internet good enough for that. And so that's part of the standardization activity that I'm going to talk about. Yeah, and what we are now trying to make work is the Internet of Things, and there are many things many aspects of this that we have to work on, but as you know, security is probably the most important one. So another question is, when we actually do this, do we actually need all of the baggage? So for instance, HTTP is the great protocol for doing web access. It has matured over a decade and has recently become another life where we now have HTTP2 and HTTP3. But to do this, you really have to be an expert. You need tens of thousands of lines of code. And it's also relatively expensive to do HTTP communication. So the question really is comparable to another question. Can you transport a sofa on a motorcycle? There is a link you can click or actually you cannot click through GoToMeeting, I'm sorry, that shows a picture of somebody actually transporting a sofa on a motorcycle. And the answer is yes, you can transport a sofa on a motorcycle, but do you want to? And more importantly, is the transport of sofas a good criteria for selecting your next motorbike? So we always have two factions here. One says IP is too expensive for my application. My hand-knit protocol is better, so MBus or whatever they are using for their environments, and that's probably true for certain applications. And there's the other faction that says IP already works, so why don't you just use it? Why do we have to change? And actually, both may be true. But let me explain this a little bit on a more quantitative scale. So this is, well, this is qualitative, but the horizontal line is supposed to be increasing acceptable complexity. So if you think about milk cartons probably could actually benefit from being on the internet, so you can find out whether you still have milk that is going to go bad soon. But really, we cannot expend a lot of money on a milk carton. So this is the kind of application that would be in the leftmost side of the picture. And then there are other applications that really don't mind having a complex system, a Raspberry Pi or something like that, that can run Linux, that requires a couple of watts to run and so on. That's on the right-hand side. But the interesting area here is the middle. So if you can use Linux, you can use all the protocols you like, including HTTP and whatever. There's not much you need to do. Then further left to that, there is the area where you can use internet technologies unchanged by adapting the implementation to what you are trying to do. And then finally, there's a pretty big barrier where to the left of it, you cannot really use internet technologies at all. So even with bespoke protocols and so on, you're having a hard time getting your application going, like in the milk carton example. And what we're trying to do here is moving that boundary. So we can probably only move it a little bit to the left, but since the number of applications you actually can do increases with decreasing complexity, it actually turns out that the overall area of the graph of the space under this red line is pretty big compared to the internet applications we already can do in the IoT. So this is really the thrust of the work here. We already know that the internet works, so the right-hand side of the picture is fine, but we also have to look at enabling more devices and smart home, smart building, smart city are areas where you really have a lot of this gray area and want to get it in there. So how do we do this? Some protocols can be fixed. So for instance, in IPv6, we have neighbor discovery, and this is a protocol that is great for networks that are not so constrained, like Ethernet, but which is having a hard time with something as like a low power lossy network. So we looked at this protocol and changed it in a few places to get a protocol that is more austere and can be used for lower power applications. Sometimes you just can remove a complex part of the protocol. So for instance, datagram TLS is a great security protocol, but X509 is relatively expensive. So if you do datagram TLS without X509, you may be able to cover applications that you couldn't before. And the third approach is to actually reuse not a protocol, but an architecture. So HTTP has an underlying architecture called Representational State Transfer. And we built a protocol like called CoAP that implements this architecture, but with a much more lightweight protocol. So let's talk about the IETF as a source of standards in this space. And first of all, I think I should be warning you a little bit. Nobody speaks for the IETF. So if you meet somebody who claims to have an official IETF position, well, maybe they are citing from an RFC, then that's fine. But in general, you should know that the IETF is just a collection of consensus processes. And people have opinions, and these opinions don't necessarily agree with the consensus items we have arrived at. So nobody speaks for the IETF, and liaisons from the IETF to other organizations are managed by a body that is related to the IETF, the IAB, not the advertisement organization of the same name, but the Internet Architecture Board. So really, IETF is about meeting people meeting that are interested in progressing the Internet of Things. These people have organizations that work for, which certainly shape this a little bit. But the foremost element of organization of the IETF is people, and we try to keep people important in the IETF. So when I say the IETF does this and the IETF does that, please take that with a grain of salt, because I'm just talking about my perspective here. So something I can talk about objectively is that the IETF has created more than a dozen working groups already that address areas that require technical work to make them work in the Internet of Things. The IETF work is structured in these working groups, and working groups are clustered into so-called areas. So the Internet areas, which is the int here in this picture, the Internet area essentially tells you how your packets get from A to B. The first, or one of the first groups that worked in this place was 6LoWPAN, IPv6 over low power personal area networks, pretty long title. This essentially made IPv6 work over low power networks. And that, of course, was a significant enabler to be able to do much of the further work. And the activities in the Internet area are about making your packets arrive in the end. There are small exceptions. 6TiSCH, for instance, is more of a systems approach, but you will learn more about 6TiSCH in this series. The next item is, how do we actually get the paths that packets have to take defined? How do we do our routing? And there is a routing protocol called Ripple that has come out of the role working group of the IETF. The third area that needs help is the applications area. We have a lot of application standards we take for granted, like HTTP, as I already mentioned. And here it makes sense to revisit the assumptions and rethink the trade-offs. So we have CoRE, which has done CoAP and related protocols. We have the CBOR working group, which has done an alternative to JSON for this area of constrained systems, as good as JSON, but much more concise. There is a group looking at semantic descriptions of things now called ASDF. And maybe another big cluster that becomes obvious here is the security area. We need to make the IoT secure, because there isn't a person sitting in front of each of these IoT devices and making sure they get all their updates and they are properly configured and so on. We have to make sure that the IoT is secure from the outset, and you know how well that went so far. So this really requires some attention. For instance, we have a form of object security in the COSI working group. We have a lightweight key agreement protocol, Lake. Suit is discussing how to do secure software updates, and RADS is discussing how to be sure that the device you're talking to hasn't already been taken over by an attacker. And finally, of course, we have operations. So how do you run these things? And we have a working group that focuses on management and operations. Okay, so there's a large body of work, and I want to use the rest of the time quickly leafing through these items. Of course, I will have very little time for each of these 15 working groups, so some I will just skip quickly. But as I said, it all started with 6LoWPAN in 2005, 17 years from ago, where we decided that we wanted to be able to use IPv6 in IoT networks. Up to then, people had said IPv6 headers are way too big. You cannot use them in a constrained environment. And we knew that this is not true, and we came up with an encapsulation for IPv6 that is saving bytes. We came up with header compression and with a network architecture that works better than the classical neighbor discovery mechanism. So what's the idea here? Well, the first one is we had to define an adaptation layer fragmentation mechanism to make IPv6 even possible on networks that may not be able to send more than 100 bytes apiece. So that's a fragmentation mechanism. We defined a header compression scheme that is much less expensive than the header compression schemes that are, for instance, used for telephony. We rethought the IPv6 architecture with respect to how do you actually enter a subnet, what is the link, and so on. We used some interesting work that was going on at the same time, and fully embraced that, and came up with a version of IPv6 NE that also has been called efficient NE. And basically the idea is to keep neighbor discovery, IPv6 neighbor discovery working as it is, but to take a few strategic exchanges like the duplicate address detection, and involve a component called the edge router in this place to do this. So we don't have to distribute this function all over the network and implement it in every single device, but we can delegate things to less constrained nodes. So that's actually a principle that really will be repeated when I talk about various technologies, because the best way to simplify code on a constrained device is to not even have it on that constrained device, but to delegate it to somebody else. So the edge router does the duplicate address detection, and also the 16-bit address allocation that we use for some MAC protocols. And it's the only node that actually needs to scale with the IoT network. And that's okay, because the edge router already needs more power to talk to the Ethernet side or the non-6LoWPAN side to talk to the rest of the internet. So we always have this one node that has a little bit more function, a little bit more power to do its work. Okay, and we updated the addressing model, got rid of some fluff, and unfortunately IP multicast is part of that fluff, but we got some of that back. And the result is something that you actually can use to do put low power devices on the network. So this is done. This has been done since the early 10s. And we have some further improvements, RC 8138 and 8505, that generalize what we have. Talking about generalizing, 6LoWPAN was just one radio, the 802 IEEE 802 15.4 radio. And at some point we decided we were essentially done with that, but wanted to look at other technologies, at other radios, and define how to apply 6LoWPAN technologies to these. So when you look at this table here, you see a orange-brown area. That's really the 6LoW area. And you see a gray area, which are links, radio technologies or wire technologies that don't really need this level of optimization, because they can work with more power. Of course, power line communication can use power. Ethernet is wired. We now have power over Ethernet. And so these are areas where we expect to have enough power to run your standard internet protocols. We are on the right side of the picture that I talked about. But in the orange-brown area, we are looking at low energy, low power devices, and each of these actually have a 6LoW instance now. So we know how to run a very energy preserving protocol over them. And that includes wired networks, RS485 networks, and not just the wireless networks in various frequency areas that you see on the top. So that's the job of the 6LoW working group, which is pretty much done at this point in time. There are still two documents that are being completed, but the popular networks have IPv6 support now. There are other interesting things happening at the network layer, and one development is that of millibit networks. So you may be used to talking about networks that do megabits per second and gigabits per second, and as I said, IoT networks often are in the kilobits per second range. We're talking about instantaneous transmission here. A millibit network is one that can provide a sustained throughput, so average over a whole day or a whole hour of some millibits per second, so less than 1 bit per second. And networks like that are known under the term LoRa and Sigfox and so on. And these need a different approach to header compression than 6LoWPAN did. So the area context state mechanism of 6LoWPAN is replaced by something called static header compression, or SHIC. And that's what the LPWAN working group does. And finally, there are two working groups, DetNet and RAW, that look at deterministic networking, so networking with guarantees, with latency guarantees and packet loss guarantees, even on wireless. That's the RAW work. So in 2013, we created a working group called 6TiSCH that essentially took 802.15.4 in the specific form of the time-scheduled channel hopping mode and defined a system standard that includes all the components, both the existing IETF components and some new components like schedule management and so on, that are needed to make this mostly deterministic network. And as I said, that will be discussed more in the webinar. So I'm going to go on to the next item. We are now in 2008, and we noticed that we actually need a routing protocol for our IoT networks, in particular for our 6LoWPAN networks. And that was created in the form of Ripple. And Ripple has a little sister called Mipple, which does some form of semi-reliable multicast flooding, but I'm not going to talk about that. But I'm going to talk about Ripple because they have a pretty interesting innovation here, which is that they really make use of the fact that IoT networks are often rooted in these border routers. I already talked about their usefulness for actually optimizing things by delegating things to less constrained nodes. And you can do this with routing. And to do this, you best build a tree, but not actually a real tree, but one with redundancy. And then ignore the green part. You essentially can define things in such a way that only the root has a full map of the tree, but the protocol makes sure that it does have that a full map, and can control the routing decisions within the network. So there were two major breakthroughs here. One is the trickle protocol as a way to reduce chatter during the time when the network is stable anyway. So if I don't have any changes, I don't need to make new routing decisions, so I can save energy. And the other one is doing these multi-parent trees, which separate local and global repairs, embrace the tree, and embrace the root as the place where routing decisions are made. So again, we make use of good use of less constrained nodes. Okay, so this was internet and routing area. Now let's quickly talk about application layer protocols, and there's a lot that can be said about that, but two working groups stand out here. One is the CoRE working group, which essentially has defined an application protocol you can use by replacing HTTP with a less expensive equivalent. This can be used in a lot of applications. Of course, there will always be applications that need something else. But if something like a web protocol works good for your application, then we have the application layer protocol for that. The second part is that we need security that is less dependent on humans in the loop. And that actually also can be stable for a while. It doesn't need a software update every 2 weeks or something like that. And this needs to consider the fact that IoT networks are multi-stakeholder. So these are the protocols, but we also have data formats. What you probably have noticed is that something called XML is now used much less than it was 15 years ago. So the industry has moved to JSON for data interchange. And JSON can be relatively expensive because it's text-based and string-based. And CBOR is essentially a binary form of JSON that can be much more frugal. Anyway, these two formats, JSON and CBOR, both come with their security formats called JOSE and COSI. And this is the basis for much of the security that we have. Of course, we also have TLS as another important component. And finally, we are looking at semantic interoperability. So you know that your moon orbiter measures in feet and not in meters. Excuse me, your Mars orbiter, so you don't crash it. And that, of course, happens in the IoT as well, that you have some data but don't know what it means. And we need support for semantic interoperability here. So let's quickly talk about CBOR. That was actually published in 2013. So this is not the time when the working group was formed, because no working group was actually needed for doing this. There was a working group formed in 2017 for doing more work, including a description language for CBOR. This has a link to a tutorial that you may want to look at. It's a 20-minute introduction to CDDL. But talking about CBOR, so we took the JSON data model, added binary data, which are sorely missing in JSON for IoT applications, and some form of extensibility, and also turned the encoding to binary, byte-oriented encoding, so it's easy to implement with little code and counting objects. So in this graph, that was a big gaping hole for a long time. Where's the binary JSON? We now have an answer. And of course, there have been other attempts to get binary JSONs going, but yeah, it's sometimes really good to have the power of an organization like the IETF for getting all the discussions going that are needed to finally come up with a good mechanism. So let's talk about application protocols again. The core working group is the one that I'm really simplifying this here. Essentially did a concise form of HTTP. And they also did something called a link format, which is a discovery mechanism that's really important in the IoT, because you cannot really groom every single device that you want to work with. And so we took the web, which of course was very successful, and translated this to a machine-to-machine environment. First of all, by adding data formats. So HTML is not so useful for talking about sensor data. I already talked a bit about data formats. The URIs from HTTP actually mostly work. So there's not much you need to do that. So the focus of the working group was on HTTP as a transfer protocol, and the architecture behind HTTP, the representational state transfer, as written up by Roy Fielding in 2000, 10 years after the standardization of that mechanism actually started. That has a number of interesting properties, and the most important property is that of loose coupling of components. So you can have components that evolve independently of each other, and that may be very important if you don't put in an IoT network just for one single application and have everything planned ahead, but have to consider the IoT assets deployed as something that is going to take part in the further evolution of your IoT network. So how do you do this? The first idea was just compressing HTTP, but that would have retained all the complexity and added the complexity of running a compressor. So that's not what we did, but we simply said, yeah, let's keep it simple. Let's design something that does all the same things we need from HTTP, but actually does provide a service and is not even simpler than that. And the result is the Constrained Application Protocol, or CoAP, with a simple 4-byte header. You know how big HTTP messages are, then 4 bytes is pretty interesting. And it also adds an observe mechanism, so you actually can be notified from a server when the data change. And that's slowly coming to HTTP, but it's usually really complex when you need to do that. So examples in this space almost look like HTTP. As an application developer, you don't really have to think about the fact that you are actually using CoAP and not HTTP. But on the wire, this looks very, very frugal. And since the architecture is the same, you also can proxy between HTTP and CoAP. So you don't have to implement CoAP on all your devices or your servers and so on. You can just use a proxy to translate between the two. And one interesting thing that the proxy can do is it can cache things which may be really great for reducing the power consumption of items, because they don't have to answer every question. And we have the observation mechanism that I already briefly talked about. Yeah, and finally, we defined a mechanism to transfer large data like software updates and so on. So the breakthroughs here were that we embraced REST, but got rid, well, not of all of it, but most of the HTTP baggage, and extended REST with observe. So that's one thing. And the other thing is that using web linking, we have a discovery architecture that we can use to set up our networks without having to involve the humans everywhere. So CoRE is still active. The CoAP base document was approved in 2013, but we are still doing a lot of things. Just published 1991-76, the resource directory document, and we are now looking at more support for Yang, which is the management architecture that the IETF has, and for more effective group communication. How can I multicast things? How can I switch on all my lights at the same point in time while doing this in a secure way? And the idea here is to reduce the total cost of ownership by using self-description and discovery mechanisms. Don't really have time to go into that. But one other important point here is that we can get semantic interoperability. So you don't get naked data, but you actually can interpret what they mean. And there is a whole group outside the IETF, the One Data Model group, that is defining data models for IoT devices, from the refrigerator to a ventilator and so on. So there's a working group in the IETF that actually defines the semantic definition format for that, while OneDM as an organization is working on the various models of IoT devices. Security is important, and it actually turns out at the time we published CoAP, we had better security than the web. The web is catching up, so that's no longer true. But the idea was an unattended IoT device really must be secure. And the initial security architecture uses CoAP on top of DTLS, the datagram transport layer security protocol. Transport layer security is also sometimes called SSL. So this is technology that many web developers understand and can apply immediately. But in the meantime, we have seen reasons to actually go into other layers with security protocols as well. We have done a little bit of IPsec support, but we particularly have been looking at doing security in the application layer using the CoAP security protocol, which is in turn based on CBOR. So this is based on the idea that we now have object security standards that we can use in the constraint space. And we also have a working group for that, the CoAP working group, which was started in 2015 and published their first RFC in 2017. Recently, we also have looked at further, again, taking the architecture from DTLS and making a constrained form of that, so we can get work done in very frugal devices, and that's the lightweight key agreement protocol, or LAKE. You also, apart from the security sublayer, you also have to think about IoT devices as a secure application. So you not only have to have the right protection for your objectives, which is hard enough, but you also have to think about protecting the right objectives in the first place. And today, IoT security often is just a Wi-Fi password. Once you have that, you have the keys to the kingdom in your home, and that doesn't even work for a 3-member family. So how would it work for larger environments? So this is where ACE comes in, the Authentication and Authorization for Constrained Environments working group. And that decided to take the popular web framework OAuth and adapt it to IoT. And these documents are currently just being published. So when you just think about the constraint aspects, you see a constraint client and a constraint server talking to each other. But in reality, you have all this structure on top of that. You have persons, organizations that have requirements on these things and that need to make their objectives known, and probably not by talking to the very constrained devices, by talking to intermediate devices, access managers, or authorization managers, the client access manager, and then the server access manager. And there's actually a theory behind that delegation mechanism. And yeah, it does get a little bit complicated at some point. But once you actually have gone through this theory, you can be reasonably sure that you have covered your bases. And of course, authentication and authorization are highly related here. It's not just that one is the prerequisite to the other, but actually the other is the prerequisite to the one as well. So again, we try to make good use of less constrained nodes. So the simple devices, C and RS, the bottom layer in the figure, they can run something that is business logic independent. And on top of that, you can have devices that actually do the business logic and prepare the decisions for those little devices. All this needs to be done in a life cycle. So you don't have a static environment. You have devices that are manufactured and don't really know yet what their purpose in life is. These get installed, which provides them with some view on their environment, but still maybe not quite their purpose in life yet. Then somebody commissions them and tells them their purpose in life. And then we can run an application for a while. Maybe we need to do a software update at some point or reconfigure the application. And finally, at some point, we need to decommission the device and make sure it no longer has the security powers that it had while it was in operation. So we have to securely decommission devices, and maybe even initiate reuse if we don't just want to throw it away, but give it some new purpose. So this is the point of view of making the IoT application work in a secure way. But there's also another problem, the IoT devices as an attack platform. So you have heard about all these distributed denial of service attacks that use web cameras and other IoT devices to run their attacks. And we are a little bit in the situation where cars were in the 1920s, where people started to learn that you actually have to regulate cars a little bit. You have to get people to fix their brakes. And that's something that the car environment actually invented car garages for. So that there are organizations that specialize in fixing your brakes, and you can go to them. Now, of course, doing this with 200 billion devices doesn't mean that you will carry your light switch to your garage to fix it. Somehow, obviously, the vendor has to do their own duty here as well, where they do that with cars as well. But specifically making sure that IoT works in environments that don't have people whose full-time job it is to manage the security of them. And if all else fails, we need jails. We need to be able to put IoT devices in environments from which they cannot do as much damage as they can if we just connect them to the internet. And an important development here is the manufacturer's usage description, or MUD. That is a short description of what the expected communication behavior of the device will be. So you know what a security camera usually does. And when you find out, oh, this security camera is opening connections to all kinds of places and sending large data streams there, then you know something is wrong, and you can firewall off that device to no longer be able to do this attack. So that's an important activity. Another important activity is making sure that software updates can be done in a secure manner and in a routine manner. So a software update should not be the catastrophic event that it often is with IoT devices today, but there should be secure over-the-air upgrades. And there actually is a working group that works on this, the SUIT working group, software updates for the Internet of Things. And these are mostly done now. So it's based on CBOR and CoC and described in CDDL. And finally, I want to mention one working group, the REDS working group, which started just 3 years ago, and tries to accept the reality that our devices are not always perfect. So it's not sufficient to secure the communication. You have to secure the devices, and as far as you may not be able to do that, you need to be able to find out when you talk to a device, does it still have its original security status, or has it been successfully attacked? So the mechanism is called attestation for that, and remote attestation is the function that is being used for that. They have finished their architecture paper. They have some protocols, but this is an interesting activity that will keep us busy for a while, in particular also with the new idea that you want to have a software bill of materials for your IoT devices, so you know what potentially vulnerable software is on them. So I have talked a lot about security here, and the reason is if it's not usably secure, it's probably not the Internet of Things. It's something that came before the Internet of Things and that we want to get rid of as fast as possible. Okay, I'm done. I think I have completely filled my slot. I don't know if we still have time for a few questions.
Thank you so much, Carsten. This is absolutely incredible. And I am going to tell you, I'm getting requests to make sure this is being recorded, which it absolutely is. And so if you have questions, please go ahead and type them into the window, and I will ask Carsten. And meanwhile, I've got, of course, quite a few. We have time for maybe a few questions. We can stay after, maybe if Carsten has a few minutes. But one of the things that occurs to me is throughout this thing, I hear you mentioning IPv6 and possibly only IPv6. So would you say that IPv6 is a prerequisite for IoT, or it is built on top of things such as 6LoWPAN, which are IPv6 derivatives?
Well, there are two aspects to this. One, of course, is that IPv6 has so many more addresses. And if we are talking about 200 billion devices, a network protocol that only gives you 3.5 billion addresses is not so great. So that's one observation. The other observation is that we actually found when we looked at the overheads of doing things, that using IPv6, things are simpler than if we use IPv4, because with IPv4 we always have to find ways around these boundaries between different addressing realms. So it's really complicated to get things going. While with IPv6, yeah, the world is relatively simple, and that's something that small, simple devices like. Of course, we make sure that our application layer protocols also work with IPv4. But I think IPv6 is really showing the right direction to go for the IoT.
So to restate, much of this will work over IPv4, but for scalability, you would suggest or recommend IPv6, or it will evolve towards that. Would that be correct?
Yes, and so some of the architectures that you can build very easily on IPv6, some of the architectures of local IoT installations that are hard to do in the IPv4 world. So it may seem simpler when you start looking at it, but when you have completed your network, you will see that it actually is more complicated.
I see. Okay, so let me see. I'm getting another a question here. Do you envision end-to-end delay requirements between a thing and something that issues a command to it, or for the delivery of a message from a thing to a recipient? I think he's talking about, I suppose, service level requirements, that type of thing. What is your thought on that?
Well, clearly, if you are running a control loop over the internet, then you have to have some idea of what's going on there. You will not get a very good result from that control loop if you cannot control your latency. One observation is that actually there are control loop algorithms that can work with worse latencies than the ones you would immediately come up with. Well, if you want to control the speed of a conveyor belt or something, you do need to have some limits to your latency, and that means you probably won't control your conveyor belt from the other side of the earth through many networks that you don't control, but you will do these things in so-called limited domains and environments where you have more control over what's going on. And the DetNet approach was to augment IP by all that's needed to get very good latency in a limited domain based on wired communication. And the RAW working group is now looking at ways to add the same kind of determinism to wireless networks. And of course, underlying technologies like IEEE 802 TSN also help getting these objectives.
Great, great. Thank you. Now I'm going to end with one final question. Please let me know if there's others, and we can tell Carsten. You know, some of the things I see about your the LBR and so forth, I just wonder, and I should have researched this, and I have not, so I'm just going to ask you, what are the thoughts around something like DHCP v6 or integrating that for IoT? I'm not sure that it is. So what is your thought on that?
Well, there are many answers to that question. Well, first of all, we have the ability to put information into advertisements in IPv6 neighbor discovery that would have been managed using DHCP or IPv4. The second observation is that DHCP often is used in situations where the person who furnishes the network for some applications wants to have control over what's going on. And the organizational structure of IoT deployments often is different. So the reasons that may cause you want to do DHCP-like things may be going away in an IoT environment. And the third observation is there are often other ways to get information that really work better than doing yet another DHCP extension. And of course, using HTTP or CoAP from a resource directory is a much more application-oriented way to get this kind of information. All that said, there are some things where actually DHCP v6 can be useful. I would say it's not so useful for getting your address, but it can be used for getting some other information. For instance, the prefix delegation, something we currently still only can do with DHCP, and that's a place where DHCP will continue to be used.
Thank you so much, Carsten. So on that, we'll thank you one final time. Thank you so much for agreeing to participate. This was, again, very, very informative and something that I'm going to need to watch multiple times to really be able to absorb all the thoughts that you've taken in. So thank you again, and everybody, we'll see you on May 12th, I hope, for the next webinar in this series. Okay, so until next time then.
Thank you for having me.